We know that, strictly speaking, Einstein's theories are wrong because they don't cooperate with quantum physics. And today I have a paper that might just provide the missing link to make them right. Let's have a look. We know that Einstein's masterwork of general relativity is, strictly speaking, wrong. We know this because it doesn't have quantum effects, and yet it needs to somehow communicate with particles that have quantum behavior. Because we know that these quantum particles create a gravitational field. We just don't know how. Physicists have looked for a theory of quantum gravity to complete Einstein's theory for 90 years. The problem is, general relativity is to high accuracy correct because those quantum effects are so small. So how could we possibly ever test them? The new paper now points out that there is a connection between the quantum behavior of space and time and the motion of stars in galaxies that no one has thought about before, which is either very exciting or a sign that everyone else carefully avoided it. To see how this works, we first need to have a closer look at Einstein's theory. In general relativity, one describes space and time by an object called the metric tensor that encodes the relations between different directions in each point and at each time. Usually, when one does quantum gravity, one looks for a quantum version of this metric tensor. One then calculates the average value of this quantity and the uncertainty that comes from the quantum effects. And from this, one then derives how the quantum fluctuations of space-time affect the motion of particles. These effects, however, are ridiculously tiny. They aren't a factor 1,000 or so too small to be measured. We're talking about something like a factor 10 to the 20 too small, like hopelessly, frustratingly way out of reach of any experimental test. The authors of the new paper now point out that this isn't so. The reason is that general relativity is a nonlinear theory. This means that there are products of the metric tensor and its derivatives in the equation. The issue with the nonlinearity is that it matters how you take the average. Suppose you have a quantity x that has some quantum uncertainty, then the average of x squared is in general not the same as the square of the average of x. The authors of the new paper now say, look, the equations for the motions of particles don't just contain the metric, they contain products of the metric and its derivatives. We should take the average of the product, not the product of the average. That makes no sense. So then they recalculate the quantum contributions using this new technique. They find that in the solar system, the quantum corrections are still ridiculously tiny. But they say, on scales of galaxies and beyond, there's a surprise, is that the cosmological constant makes a contribution to the quantum corrections that can become large. The first author, Ben Koch, says in the press release, on very large cosmological scales, precisely where major puzzles of general relativity remain unsolved, there is a clear difference between the particle trajectories predicted by the quantized new equations and those obtained from unquantized general relativity. I find this very interesting because we have this alternative to dark matter called modified Newtonian dynamics. That's a correction to Einstein's equations, and that also scales confusingly with the cosmological constant. No one knows why this is. We just know from the data that that's the case. That said, the concrete equation that they get does not directly look like modified Newtonian dynamics. The issue is that, you see, this is not a theory of quantum gravity. It's a way to link a theory of quantum gravity to observations. This formalism still needs an input that tells us what the quantum fluctuations of space and time are. For this, luckily, one doesn't need a full theory of quantum gravity, one just needs a plausible description of the quantum state. However, they didn't do that in the paper. Basically, I understand this paper as a first step in what could become a very interesting research direction. On the bullshit meter, I give this a 3 out of 10. I think it's formally correct, but they should have made more effort to quantify their results. In particular, I'm not at all sure that it's correct what they say in the press release, that there is a clear difference at large distances. At least I didn't see it. The reason I'm telling you about this is that if there ever is a breakthrough in the foundations of physics that'll get us out of this stagnation, it might look like this: a way to connect quantum gravity to modified gravity and to maybe resolve all these tensions in cosmology. And if this turns out to be wrong, that'll still fit nicely with the other research in the field. Microplastics are everywhere and they're making us ill. I'm sure you've seen this in the headlines in the past years that seem to get increasingly hysterical. I think these worries are exaggerated, and today I want to explain why. Microplastics or nanoplastics are grains of plastic of micrometer or nanometer size, respectively, that have spread all around the world. They are created when larger pieces of plastic decay and gradually grind down to tiny pieces, kind of like YouTube videos if I think about it. Microplastics have been found literally anywhere: in the Sahara, in the Himalayas, in the Arctic. They're in the water, in the air, in the ground, and in our food. That sounds pretty bad, but we're surrounded by lots of other small particles of organic and inorganic origin, from leaves to dust, and we constantly inhale and swallow those too. Plastic is made from fossil fuels and is of a different chemical composition, and many plastics contain unhealthy chemicals. So it's plausible that micro and nanoplastics are unhealthy, and they probably are. I want to be clear that I certainly do not deny they are unnatural and likely unhealthy. It's just that at the moment the evidence is poor. Let me just read you from some official governmental reports on the matter. The UK government had a committee look at the risk from small plastic particles last year and concluded currently a comprehensive risk assessment of the potential health effects from the inhalation of nano and microplastics is not possible due to significant evidence gaps. The German government looked at the question too and reported just in December that no causal relationships have been proven to date between the uptake of microplastics and health effects. The US Food and Drug Administration says current scientific evidence does not demonstrate that levels of microplastics or nanoplastics detected in foods pose a risk to human health. And the Irish Environmental Protection Agency concluded the same thing. The lack of evidence around the effects of microplastics and nanoplastics in human populations means that we cannot fully assess the risk. This is consistent with what meta-reviews have found, that most of the studies on the subject differ from systemic problems, small samples, and possible contamination. So what the hell is going on? Why are there all these big scary headlines? Because we don't know yet does not travel far on social media, and the headlines come from studies that found truly alarming results, which were later criticized. For example, last year a paper published in Nature Medicine reported micro and nanoplastics in human brain tissue. The study was quickly questioned by colleagues, saying that the authors might have mistaken fat tissue for plastics. A 2024 paper reported that microplastics had been found in plaques that can clog arteries. This paper was swiftly criticized, among other things, because, quote, many factors suggest potential external plastic contamination of samples. A 2022 paper that reported plastic particles in the human blood was also criticized on the ground that, quote, the hypothesis is not supported by the data. And those are only some examples. Most of the papers in this area have the same problem, which has been pointed out in multiple reviews, that microplastics are difficult to measure, the risk of contamination of samples from lab equipment is high, and there are no standardized methods. Worse, the currently most widely used method is unreliable, as was argued in a recent paper that said it's currently not a suitable analysis method for plastic in biological matrices. A recent review says despite growing concern, there are currently no standardized methods for assessing the human health risks associated with microplastics exposure, and another one similarly found, lack of standardized testing hinders accurate assessment of health impacts. Okay, I stop there. I hope this was sufficiently many quotes to convince you that the microplastic headlines are almost always exaggerated. I'm not saying that there is nothing to worry about, it's just that the evidence simply isn't there, at least not yet. Why is this happening? I think one of the contributing factors here is a vicious loop in which the media coverage leads to public attention, which leads to better funding for the research. This leads to more studies, but many of them are of questionable quality because they'll get attention regardless. This is a problem that you generally must expect in any research area that attracts public attention, whether that's better batteries or mRNA or dark matter. The more public attention, the more junk will be published on the topic. So yes, microplastics may well be a problem one day. Right now, the bigger problem seems to be microevidence. Wild things have been going on in mathematics with the use of artificial intelligence. In the past months, we've seen lots of reports that AI is suddenly solving theorems that have been unproved for decades and making other advances. And on the one hand, we now have people who say that maths will be commoditized, as the current buzzword has it, that everyone will be able to do professional maths with AI. On the other hand, we have people saying most of these so-called proofs were just rediscoveries or actually wrong. What are we to make of this? I've had a look. This recent episode began in October 2025 when Kevin Weil, Vice President of Science at OpenAI, posted on X Twitter that GPT just found solutions to 10 previously unsolved Erdős problems and made progress on 11 others. This was then echoed by several other researchers at OpenAI. But what the hell are the Erdős problems? This is a list of about 1,000 maths problems, 60% unsolved, compiled by the Hungarian mathematician Paul Erdős in the past century. They're in areas like number theory, combinatorics, graph theory, set theory, and some other fields about which the average person says, wow, and then backs out of the room. There is no official list. There's just a website maintained by a mathematician, Thomas Bloom. So the Erdős problems are not like the millennium problems. They are mostly not considered to be of high relevance, and many have remained unsolved, not because they're so difficult, but because no one really cares. Still, it'd be interesting if ChatGPT had solved some of them. Yet it turned out that it had simply rediscovered solutions in the literature which had not been listed on the website. Thomas Bloom clarified, GPT-5 found references which solve these problems that I personally was unaware of. Demis Hassabis from Google DeepMind somewhat uncharacteristically commented, "This is embarrassing." Personally, I think that the OpenAI people should have checked themselves whether the proofs were actually known in the literature. All they had to do was to ask ChatGPT. But if even the guy who maintains the website didn't know of the proofs, it's still a pretty amazing search tool. There was another team of mathematicians who used ChatGPT to find a counterexample to one of the Erdős problems, but they noticed themselves it was a rediscovery of an earlier proof. We saw another proof pop up on the archive, which was suspected to be ChatGPT written and was swiftly withdrawn by the author. The OpenAI guys later deleted their posts, but you can see why the AI maths enthusiasm faltered somewhat during this episode. That wasn't all that happened though. We've also seen some examples where ChatGPT seems to have made a useful contribution to real proofs, albeit moderate and nothing of major impact. By January, however, ChatGPT did eventually also solve one of the Open Erdős problems, which Fields Medal winner Terence Tao called a milestone in the application of AI tools to these problems. So what are we to make of all this? One interesting thing that we're seeing clearly is that all these examples use ChatGPT Pro in particular, none of the other AI tools. This agrees with my personal experience. ChatGPT Pro is well ahead in maths compared with Gemini, Claude, and Grok. It's not a little bit ahead, it's a completely different level. In a recent report, OpenAI said they now have almost 1.3 million weekly users sending about 8.4 million messages on advanced maths and science topics, about half of which are mine. That's up almost 50% from last year. Topics include everything from analyzing data to debugging code to planning experiments. The other thing we're seeing here, I think, is some initial confusion about the capabilities of the models and how to deal with them. AI models are extremely good at finding relevant information in the published literature. They sound somewhat lame and is the reason why there is a risk they just rediscover forgotten proofs, but it's also why they can help solving a problem, because maybe the solution is to apply some already known insight. And I think this is the stage we're at now. It's 2026, and the hottest new mathematical technique is finding the PDF. Will mathematics indeed become commoditized? I still think that with the current large language models, no. Again, I'm going here by my own experience. ChatGPT now does computation with SymPy, which avoids a lot of errors, but its logical reasoning continues to be weak. If it comes up with a proof, that's as likely to be correct as wrong. And I mean, it makes really idiotic mistakes, such as using a bound the wrong way round or just inventing a convenient assumption. At the moment, I think it's best understood as a discovery tool. But I actually do believe that mathematics will eventually mostly become something we can let AI do, and most human mathematicians will become obsolete, the same way that human calculators have become obsolete. And that will not be a minor change, but it'll take a few more years. And then mathematics will get a new research area called premium support. Thanks for watching. See you tomorrow.